welcome to the video on the chain rule. So we've learned about the chain rule for paths, which is when we have a multivariable function with a path inside determining each of the components, right? And that path is dependent on or has one parameter, such as t, right? So before we had some kind of like f of c of t, right, where f is a multivariable function, like an x, y, z, and then this path here was given by c of t is equal to an x of t, a y of t, and a z of t, right? So this was a path, and then this was our multivariable function, and we're just gonna, what we did was stick these into those spots there. So f ultimately depends on t only, t alone, okay? So that's what we've done, and then we use the chain rule for paths, right, to differentiate our f of c of t. But now what we're gonna do is start with something a little bit different. So suppose we have some kind of, again, we're gonna start with a multivariable function. So this is f of x, y, z, so this is multivariable, okay? And now we're going to say, and x, y, and z are also multivariable functions. Multivariable functions. And what do I mean by that? Instead of x, y, and z depending on one variable, such as t, now they're going to depend on like s and t. And then we'll have a y of s and t and a z of s and t. Okay? So this isn't, it isn't just x of t, y of t, or z of t anymore. Now we added in that s, another independent variable. Okay? So now our composite function looks like the following. So composite function, it's going to be f of x of s and t, y of s and t, and z of s and t. So we have a lot more variables going on here, right? And it's important to note that s and t are both independent variables. Okay. Okay, so basically, with this version of the chain rule, we're going to figure out how do we differentiate this guy here, okay? So what we can do, well, I'll write it on the next slide, okay? So we're starting with this, our composite function, which looks a little bit more monstrous now, right? Now that we added in that s. So anyways, what we're going to do to take the derivative of this is, since we have these two independent variables, s and t alone, or separately, right, what we can do is express the derivatives of f, of this whole entire thing, with respect to each of the independent variables separately, okay? So the first thing we're going to do, so we have to take a partial derivative, right? So let's focus on the s first. If we try to take the partial derivative with respect to s of f of x of s and t, y of s and t, z of s and t, there we go. Then what we have to do is basically we start from the f at all times, and we're going to have, this is kind of it's going to grow from the chain rule for paths. So what we're going to have is the gradient of our f at a certain point, right? And then dotted with, because the gradient is a vector, right? So that's a vector, and we're going to dot that with the vector that we get by differentiating c, or taking the first derivative of c, of our path here, and this is with respect to s, okay? Alright, so in a more expanded form, this would look like, c, something to note is that c of s and t looks like x of s and t, y of s and t, and then our z of s and t. So how are we going to figure out both of these? So like I said, we're going to expand on the next line. So this is going to be equal to, the gradient of f at some point is going to be f, so we kind of make the jumps, right? So our first partial is going to be partial f, partial x, okay? And then our next jump is going to be partial f, partial y, and the last one's going to be partial f, partial z, Okay, so here you see how in this first step, by taking the gradient of f, we just differentiated. We took the partial derivatives with respect to each of the components, whatever's in that spot, right? So in this case, it was the x function, the y function, and the z function. Okay, we didn't deal at all with the s or the t at all. Okay, that's where the second part comes in. So we're going to dot it with this second thing, this c prime of s, which this is where we'll jump to the s's. So now that we're at, so like at this point we're already at the x, at this point we're already at the y, we already jumped there, and at this point we're already at the z. So what we're going to do is finish it off. So we're going to start from the x, so we're going to take the partial derivative of x with respect to s, because that's the one that we're looking at, right, the s. So this is going to look like the partial of x with respect to s. And these, we have the curly d's here, or the partial, denoting a partial derivative, because x is now a multivariable function and not only a single variable function. So we have to have that curly d to specify which variable we're going to. Okay? And then for the next component, we're going to start from the y that we're already at, and we're going to take the partial derivative with respect to s. So we have partial y, partial s, okay? And for the last one, we're going to jump from the z to the s. So that'll be partial z, partial s, okay? So that's basically it. These, just a side note, these ones here, when you're dealing with the outside function, with the outer function like our f, these are called the primary derivatives. That's just a terminology thing I thought I would throw in. So these are called the primary derivatives, okay? And then anyway, so when you take the dot product, this is what we'll end up with, is partial f, partial x, partial x, partial s, okay? And then we're going to add that to partial f, partial y, partial s. And last term, partial f, partial z, and partial z, partial s. Okay? So that's basically it. That is the chain rule. What we did here, if you see in the formula, it's kind of like these, the partial x's can cancel out the partial y's and the partial z's. So this kind of, well, technically, that wouldn't be correct, but like, if we were to look at it, you could kind of do that, sort of. But anyways, conceptually, what we're doing here is we're starting from f, our outer function, right? And we're going through the x, y, and z functions to get to the s's that we want, okay? So that's what's going on here in the chain rule. All right, and similarly, let's look at what would happen if we tried to take the partial derivative with respect to t. So let's try it here. So we have our function, so it's going to look like this, and then our z of s and t. Okay, so if we did that, then we get that this is equal to the gradient of f at a point dotted with c prime of t now, with respect to t, okay? So this is going to be, when we expand that, the gradient of f, we're going to have the same exact primary derivatives, right? Because we're still jumping from this original f to each of the components first. So that would be the x, the y, and the z, right? So we're going to have partial f, partial x, okay, comma, partial f, partial y, comma, partial f, partial z, okay? So here is where the difference comes in. Now that we're at the x, y's, and z's respectively, now we have to get to our final variable, which is the t. So now we're going to jump from x to t. Okay, so that means we have to take the partial of x with respect to t, and then the partial of y with respect to t, partial y, partial t, and lastly partial z, partial t. Partial z, partial t. Okay, and again, just a reminder, in this second vector here, we had to use the partial like notation, right? Not singular or the normal d's, because again, our x, y, and z are now multivariable functions of both independent variables s and t, so we had to specify which one we wanted to hone in on or focus on, right? So in this case, it's a t. And then the last line, if we just compute the dot product, what we would get is partial f, partial x, partial t, plus partial f, partial y, partial t, and lastly, partial f, partial z, and then partial z, partial t. Okay, so in this case, we are going through our f, going through each of these f's And, well, we're starting at f, we're going through the x's, the y, and the z in order to get to our final result, which was the t, right? So anyways, so this is the another example of the chain rule.